Welcome to Fun Homework Problems Time with Jason Barnett. I am your host, Jason Barnett, and let's do some problems. Find the second derivative. We're looking at 192. Find the second derivative. Remember, we can write the second derivative in that form for the given functions. Y equals sine of x times cosine of x. So to find the first derivative, well, to find the second derivative, we need the first derivative. We're going to have to use a product rule. So, if f is sine, that means f prime is going to be cosine. If g is cosine, that means that g prime is going to be negative sine of x. You don't have to do this, but I just think it makes it a lot easier to not make a mistake, a lot easier to have clear work. The product rule says f prime g plus f g prime. The order doesn't matter, but I like writing them in this order because it's the same order as the quotient rule. And in the quotient rule, the order does matter because one of them is a negative. But addition is commutative, is the word, which means the order doesn't matter for addition. Multiplication, also commutative. Division, not commutative. All right, f prime is cosine of x times g, which is cosine of x. We've seen something like this before. Plus f is the sine of x times g prime, which is negative sine of x. So all in all, that gives us cosine squared minus sine squared of x. This is almost really nice, right? If that were a plus, then it would simplify to 1. So this is y prime, sorry. So y double prime, and again, we can't really take the derivative in this form because we're missing something called the chain rule. And we do that in 3.6. It's coming up. I've been wanting the chain rule for so long, but this book kind of does it pretty late. I love the chain rule. It's very, very powerful. So we can't really take the derivative in this format. So we're actually going to take the derivative of this format. All right, we're going to use the product rule twice. All right, I'm not writing it out again for 2 more products. I tell you guys to show your steps, and then I'm like, we already did it once. That's enough. So derivative, let's take the derivative of this first. The derivative of the first function times the original second function plus the first function times the derivative of the second function. So that's the derivative of that. Now let's take the derivative of this. The derivative of the first function times the original second function plus the first function times the derivative of the second function. I'm moving so much today. We should have just it's time for Ghost Jason. Okay? Now I don't have to move. There we go. This is the solution. And now we can just simplify a little bit. So notice that these things are the same. Minus sine cosine, minus sine cosine. Wait. Minus sine cosine. Minus sine wait, they're all literally they're all the same thing. So we have 4 minus sine cosines. All right. Oh, I'm still writing in red. Yeah, later on when we get the chain rule, we'll say that the derivative of this is 2 cosine of x times negative sine of x. And the derivative of the other one is negative 2 sine of x times cosine of x. That's another way to see where that's a chain rule right here. We haven't done that yet, but you see that it gives you the same answer. All right. Do another one, 198. 198, the name of the freeway I grew up nearby in Central California. Find all x values on the graph of this between 0 and 2 pi where the tangent line has slope 2. All right, our function is x minus 2 cosine of x. That's not how you do that. X minus 2 cosine of x. Oh, it's really weird on the white background. You can barely see me. X is between 0 and 2 pi exclusive. And specifically, we want slope of 2. So let's look at Desmos and get an idea of what we're looking for. X minus 2 cosine of x. And we only care between 0 and 2 pi. All right, we're going to have to zoom out a little bit. All right, so we're looking on this interval. Where is the slope 2? And it's kind of hard to tell because our scale isn't equal. Actually, it's really hard to visually estimate it because our x scale is different from our y scale by quite a bit. But here, all right. So because of that, let's actually change. There. Now each bot. Let's. I can't decide how I want to fix this. You know what? We're not going to fix it. We're not going to fix it. I give up. Let's just do the problem. We want to find slope is 2. So what is the slope? The slope is the derivative. All right. Derivative is just 1 plus 2 sine of x, because the derivative of x is 1. Derivative of cosine is negative sine. The negatives cancel. When is that equal to 2? Well, we get to, again, solve a trigonometric equation. Subtract 1 from both sides, and then divide by 2. You're going to get, this is when the sine of x is equal to 1/2. Remember, to solve trigonometric equations, you have to isolate the trig function, and then solving it from there is a little bit more complicated. So again, remember your all squids train camels. When is sine positive? Sine's positive in the first quadrant and the second quadrant. So there should be 2 answers in the interval 0 to 2 pi. The first one you can find with inverse sine if you wanted to, or we can use reference triangles. 30, 60, 90. Looks like this. When is the sine 1/2? 30 degrees. So we're going to use radians. X is going to be 30 degrees or pi over 6. And then we also want the 30-degree reference angle in the second quadrant. That's going to be going pi units and then going back pi over 6. So that's 6 pi over 6 minus 1 pi over 6, 5 pi over 6. Those are the 2 angles. Those are, the 2 angles are the 2 x-coordinates that we're looking for that give this function a slope of 2. At pi over 6, it is around 1/2. Oh, the slope is about 2 right here. And at 5 pi over 6, which is like 15-ish over 6, it's like about 2.5. Here and here should have about the same slope. And it should be 2. And those are the only places with that slope on this interval. And now we can make this work, right? The scale, just stretch this out a little bit. All right, now the scale, now we have actual, like, roughly square boxes. But at 1/2, the slope should be about 2. And then also at about 2.5, the slope should be that same value of 2. Here it's steeper. And again, like, we would also have one around here, but that's not in our interval anymore. This is over 2 pi, right? Okay, that's this problem. Let's do another one. 205. I've never lived near a 205 freeway. I think I've lived near a 210. 205 says, use the quotient rule to derive the given equation. So this is almost exactly like what we did in that in 3.5.3, where we derived the derivative of tangent. So this is just going to show where the derivative of cotangent comes from. Now it's almost exactly going to be the same. I'm going to do 206 instead. Let's show where secant comes from. All right, so the derivative of secant, that's the derivative of 1 over cosine. Now you could write this as cosine in the negative first if you had the chain rule. We don't have the chain rule yet. Very sad about that. But in the meantime, we can use the quotient rule. So f of x is equal to 1. F prime of x is equal to 0. G is cosine of x. G prime is negative sine of x. Oh, there's totally enough room to write that. The quotient rule says low d high minus high d low. Square the bottom and away we go. F prime is 0. So that whole first term is 0 minus f, which is 1, times g prime is negative sine of x, which is that sine, divided by g squared. And g is cosine, so divided by cosine of x squared. We have sine of x over cosine squared of x. And you might say, slow down, Jason. This is not the formula you gave us. You said the derivative of secant was secant tangent. This isn't secant tangent. Or is it? It is, right? This is just 1 over cosine times sine over cosine. Well, what is 1 over cosine? That's secant of x. Sine over cosine is tangent of x. So we did indeed prove that the derivative of secant is secant tangent. I hadn't done that for a while, so, I was a little nervous when I introduced the video. It turns out I was right. Turns out. Because I don't include stuff like that on my notes, just like what I want to talk about. All right, there we go. That's how you prove these ones. Last one, 212. Wow, we don't have an hour-long video. How sad. Who knows, maybe this last problem will take that long. 212 says find the second derivative of secant plus cotangent. Find the second derivative, and again, you can write it in either form. This is Leibniz notation is what it's called, named after Gottfried Leibniz, one of the co-founders of calculus. Co-founders? You don't found calculus. Except maybe in the literal sense of finding it, like calculus always existed and then they just figured it out. They found it. I don't know. This is a stretch, Jason. So derivative of secant, we just showed that it's secant tangent. Don't forget your x's. A lot of times verbally we'll say secant tangent when we mean secant of x, tangent of x. Plus cotangent, the derivative of any co-function is negative. Specifically, that's going to be negative cosecant squared. You can check your notes. Hopefully that's what I have. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. All right. In fact, you really only have to memorize like 3 of these. And then for the other ones, actually these three are the only one that you have to know, because if you know these 3, then to find the co-functions, just add co's everywhere and put negatives. Right? Sine is cosine. So cosine would be co-cosine. Wait, all right, never mind. Co-cosine isn't a thing, Jason. But the idea is solid there. They're all related. How did this guy get over here? What is this page doing here? All right, that's the first derivative, and then we have to take another derivative. So we're going to have to use a product rule. Derivative of the first function is secant tangent. Derivative of the second function is secant squared. Again, that's the derivative of secant. That's the derivative of tangent. And we have to use the product rule. So derivative. Wait, whoa. Jason, what are you doing? Product rule is derivative of the first, which we've done, times the second, plus the first times the derivative of the second. All right. All right, this is f prime g. It's f g prime. Woo. And then we're going to have to, again, write this. It's cosecant x times cosecant x right now because we don't have the chain rule yet. Ugh, darn you, chain rule. You're so useful. We're going to have to use the product rule again. So minus derivative of cosecant is negative cosecant cotangent. And the cosecant is there from before. Now we're going to have the same thing for the second part. I mean, it's going to be the same thing. You just make it 2. Like so. And then the negatives cancel each other out. I'm kind of skipping a lot of steps here. All right, so what do we got here? The first thing simplifies to just secant of x times tangent squared. The second thing is secant cubed. And the last thing is 2 cosecant squared cotangent of x. That looks weird. And I did a lot of weird stuff here. Let's really quickly check our work. So first derivative is secant tangent minus cosecant squared. That's pretty straightforward. Second derivative needs the product rule on both. Second one can also be done with a chain rule. That'd be negative 2 cosecant of x times cosecant cotangent, which is what we have. And then the negatives canceled for this guy, so that one's right. In the first one, we need to use the product rule here. Product rule here. Derivative of the first is secant tangent times the second, good. Plus the first, secant times the derivative of the second, that's good. Then we just combine them like so, and it looks pretty good to go. Another way that you can kind of do a little gut check on this one is you could just find a tangent line. You just plot y prime. Right, y prime. It doesn't like it like that. If we plot y prime, that's going to be secant tangent minus cosecant squared. Oh, it doesn't like the cosecant squared either. Or wait, what is it unhappy about? Oh, it doesn't. Whoa! Huh. All right, and then we could just find like a tangent line at some nice point. Like look at, actually it doesn't matter where we have the tangent line. But the slope is just going to be, let's just choose 1. When x is equal to 1 is the second derivative, which is the derivative of the first derivative. Secant of 1 times the tangent of 1 squared plus secant of 1 cubed plus 2 cosecant of 1 squared times cotangent of 1. So that should be the slope when x is equal to 1. So y minus when x is equal to 1 is going to be secant of 1 tangent of 1 is just the y prime equals the slope, which is about this, times x minus x coordinate. Now let's zoom in, see if we're doing it right. I said let's zoom in. Wait a minute. What's going on here? Here we go. Do we indeed? Oh, look at that. If my eyes don't deceive me, that is a tangent line. So I just used our first derivative. Blue is the first derivative. And then I used the derivative of the first derivative, which was the second derivative, to find the slope of the tangent line. Because the tangent line of the first derivative gives, like, the slope of the tangent line of the first derivative is the second derivative. So that's one way to check another way to check your work on these. All right. That's pretty much it. I am going on a walk in 30 minutes and the rain just started pouring down. That's actually one of the things I like about moving to a new place. I don't have an upstairs neighbor, which has a couple benefits, but one of them is that I can hear the raindrops on the roof. I like that sound. Anyway, good luck. Bye-bye. Have fun.